So my name is Ian Perez. I'm from Amazon Web Services. I'm part of the global business development team. They're focused on IoT. And today's topic is really talking about how to extend machine learning to industrial applications at the edge. And the goal here is not really to go super deep on specific AWS services, but really just to provide some industry-relevant context in terms of how AIoT are kind of morphing into some very relevant or prescriptive use cases, if you will, for industrials. So as far as the agenda, and I'll try to cut through most of the fluff here and get into the more meaty part, but really just kind of level set on what are some of the digital transformation use cases that we see for industrial IoT, and more specifically, the confluence of AIoT. We'll talk a little bit about what is the recombinant value of AI and IoT together for those use cases. I'll speak to a little bit of the reference architectures. Again, not meant to be super prescriptive or rigid, but at least give you an idea of how do you actually take building blocks at the edge as well as building blocks that are available on the cloud side to actually produce something of value in terms of a supporting architecture. And then I'll talk a little bit about some customer success stories. Customers that have actually taken AIoT to the next level for their specific use cases. And then the key takeaways is just some reference material. I'll try to keep some time for questions at the end. If not, you'll find me outside. We can always have a private Q&A session outside. So as far as just doing a quick pulse check on Industry 4.0, and a lot of the terms that are being used, whether it's Industrial 4.0, Society 5.0, some of the macro trends that are obviously amounting to the status quo you see here. The actual change or shift from mass production to mass customization. It's not just sneakers. Now you're seeing it in cars. You're seeing it in even industrial equipment that's being provided to industrial manufacturers. The traditional business model of going from buying towards leasing, paying as you go. And obviously more autonomy being worked into kind of the full life cycle. If you think of a digital supply chain from creating goods to delivering those goods, you're seeing a lot of autonomy come into play. And that's, quite frankly, affecting pretty much all sectors. I don't think there's any industrial sector that's untouched, whether you're in discrete manufacturing or process manufacturing, mining, energy, oil and gas, or agriculture. We're kind of seeing the promise of all these things coming together, specifically democratization of sensors, cloud computing capabilities, AI, ML specific powered analytics, and people to kind of really just improve overall productivity and efficiency. And so a lot of times we get asked, well, what are the specific use cases that customers from an AWS perspective are focused on? And these are just a few examples. I'm not going to go super deep on all of them, but these, I think, are fairly representative of what we see across all those different sectors or segments. Predictive maintenance, quite significant, simply because it impacts the bottom line quite a bit for large, multinational manufacturers. Operational plant equipment enhancement kind of goes alongside with that. We're also seeing quite a bit of innovation or focus on worker safety. Obvious advantages that comes with. But then there's other things that I think are kind of the next wave, or they're certainly considered to be quite transformative and high priority. Things like product design enrichment or digital supply chain optimization that are specific from an AIoT perspective, a little bit further up the value chain, and also a little bit further up in terms of difficulty of how to kind of engineer AIoT for those use cases, and I'll talk to that in a little bit. Regardless, of what is kind of leading the digital transformation initiative, for a given organization, we find that at the end of the day, our customers are looking for favorable business outcomes, and whether that's on the left-hand side where they're looking to introduce new services or new service models, new products that actually add to the top line, in other words, increase revenue growth, or perhaps they're more operationally focused and trying to bring down operational costs and increase efficiency. These aren't mutually exclusive, by the way. We have a lot of customers that are attempting to do both. At the end of the day, it's really that specific business outcome that should be framing the overall adoption strategy for AIoT. And so it goes without saying that nobody just buys AI or IoT unless you're an academic or research type of organization. More than likely, you're looking at these to actually solve for a specific business outcome. So let's look a little bit at the recombinant power of AI and IoT, and I'll start with just kind of going over this what I perceive to be this progression towards industrial aware AI. These are just my plots here. This is not a standard per se, but just based on the evidence of what we see customers doing. There's kind of two key axes here to pay attention to. From a cognitive perspective, things that are either mundane or routine to things that are not non-routine, and the level of complexity in terms of building, training, and optimizing machine learning models to actually focus on these specific use cases. And I've tried to kind of capture, the plots in just kind of broad brackets. There's kind of the easier to implement use cases such as operational equipment enhancement, predictive maintenance, scrap and leak detection, et cetera. These are things that generally, a supervised learning approach will actually help solve for quite easily. Some nuance there, obviously, depending on the very specific use case. But then as you kind of get to some of these other use cases where you're looking at, digital supply chain optimization, not only within your organization, but across your partner affiliates, or really doing AI-powered process optimization where it's, more or less hands-off, or perhaps with the help of kind of human observation. These are things that start crossing into more of the unsupervised or perhaps reinforcement learning camp, or even semi-supervised learning camp, where it's a little bit more difficult to engineer. And that's not to say we're not seeing evidence of progress in those areas, but it definitely speaks to kind of the the overall complexity of implementation. And so the question is why. The reality is that machine learning in and of itself can be a bit of a challenge, a steep learning curve for kind of the everyday developer, if you don't come from an AI or data science background. But more specifically, when you're talking about machine learning on top of machine data, which is what we tend to see in more industrialized IoT environments, it's more of a messy world, right? You're dealing with volume, variety, veracity of data that just makes that ML model creation and optimization process a little bit trickier to solve for. And so doing it for one machine or one component of, let's say, a manufacturing facility may sound rather trivial, but when you start expanding that to multi-stage or multi-phase manufacturing processes and multiple manufacturing facilities, you kind of start to see where this can be a little bit overwhelming. And so, when we talk about the specific ML types or methods, I should say, we try to encourage customers to basically, start with something that is kind of proven. The algorithms, for the most part, are pretty well proven and robust, but actually learning how to actually build a model, from meaningful data or specific data that's coming from a customer environment tends to be what we kind of bring into question. And so in the case of supervised learning, something like regression based algorithms are usually really a good starting point, where we're dealing with predictive maintenance use cases, for example, right? Providing a predictive set of inputs that should be able to forecast or at least call into question a certain anomaly that's not fitting from the results. Same thing for classification models. In some cases, we have, I'll call out an example customer success story where, you have a pulp or paper manufacturing facility, multiple sensors, multiple actuators, multiple systems that are kind of making up that production line. In some cases, all those variables being able to kind of reduce the signal-to-noise ratio. You want to use something like a classification-based machine learning model to help with that. And then, as I said, crossing into more of the advanced use cases where it's taking advantage of unsupervised machine learning. This is where we're really starting to see a lot of experimentation specifically for some of those use cases, such as automated design enrichment or automated design optimization that traditionally has been done by hand or human effort alone. So again, not meant to be a super deep dive on the specific algorithms themselves. I think those are fairly well understood and robust, and from an AWS perspective, we support and provide a lot of those models for general use. One thing that we'll call out here as yet another interesting I guess adoption wave within industrial is the use of computer vision. So where we might be kind of splitting the dominant trends in terms of predictive analytics or predictive maintenance in industrial, we do see quite a bit of adoption of computer vision. And so one of the examples here that we've kind of managed to package up into a prototype is the idea of a cloud-connected conveyor belt. That can do object detection at high frequency, and the use cases for this are kind of manifold. It can be for inspection, quality inspection of finished products or semi-finished products as they're rolling off the production line. It can be for sorting, number of different applications here. And so we collaborated with our partners NXP and Toradex on this, and so this is just kind of a quick example of how I know a lot of us here like to tinker and create different prototypes. So this is an example of how you can actually take different off-the-shelf components. In this case, we're using the Toradex Apollos module with an onboard NXP IMX8 QM application processor. We have a basic MIPI camera that's connected to it, a miniaturized conveyor belt, some linear motors with controllers, and the idea is obviously we're, in this case, using pasta, could be nuts and bolts or some other more, I guess, industrial focused type of object. But the idea is that we're using computer vision to actually monitor the actual types of, in this case, the types of pasta that are kind of going through the conveyor belt. And again, it could be something more robust than just object identification. It could be looking for specific attributes, perhaps if the pasta is broken or something to that effect. And so the idea here is being able to actually not just provide a demo for the edge components or a reference design for the edge components, but there's quite a bit of additional cloud components that kind of pull this thing together. And the things I'll call to your attention are, in terms of creating that object, or excuse me, creating that model and optimizing it to be deployed on edge hardware, we're using cloud services such as like Amazon SageMaker, which helps you, it can help you do the basic labeling of your data, building the actual model, training the model, and then more specifically, optimizing that model to run on edge-specific hardware based on the architecture profile, hardware profile. We're also using things like AWS Greengrass, which is runtime for running your application logic at the edge. Could be inclusive of the actual ML inference application that you're running at the edge without necessarily requiring connectivity back to the cloud. And so, these things also, the demo also has provisions for basically a local user interface as well as a cloud backend user interface. So one of the things that we highlight here is that the local user interface, by virtue of running on a Greengrass-enabled device powered by Toradex, doesn't have any dependency on connectivity back to the cloud. So this is a kind of an autonomous UI that is available, let's say, to the plant manager or whoever's monitoring kind of the conveyor belt process on premises. And then there's a web UI that could be managing the overall health of the system across many deployments that might be geo-dispersed. And so a little bit deeper look at the solution architecture for this, just again to kind of solidify or codify how these different edge and cloud components come together for a computer vision solution that's supporting industrial. I'll just kind of walk you through this. On the bottom left, you see the edge component. So again, this is the Toradex Apollos with the NXPI MX8 chip on there. That's running an industrial grade version of Linux, which is Horizon OS. That is also hosting the Greengrass Edge runtime software, where you can deploy your application logic for various use cases, in this case object detection. You run that application logic completely autonomous and independent of cloud connectivity. And then that edge, if it's one location or many locations, that edge component, if you will, is ingesting data through AWS IoT Core over MQTT. That data is then used to actually build and train the model in Amazon SageMaker with built-in Jupyter notebooks. And so that can be, I'll come back to kind of what that virtuous cycle might look like in terms of constantly ingesting data, retraining your model, optimizing the model, and kind of deploying it and just kind of doing that over. And then on the right-hand side, top right-hand side, you see kind of more of the web application components that are servicing the actual dashboard, not the local dashboard, but the cloud-powered dashboard that's using things like Amazon API Gateway, S3 for storage or for static content serving, and CloudFront for kind of geo distribution. And so these kind of give you a rough idea how you can kind of stitch together both the edge and cloud components to have basically a coherent object detection type of solution that's deployed using the components that you see here. And I probably didn't mention it before, but this was using standard TensorFlow MobileNet algorithm for the object detection. You obviously have your choice. There's absolutely no religion in terms of which language you want to program in, or if you want to bring your own algorithms versus using the ones that are built in, entirely your choice. So I do want to focus a little bit on the kind of this virtual cycle that I mentioned. What I just covered in terms of that reference design might be great for a greenfield opportunity, but you might have brownfield scenarios where there's already existing data that's being ingested or captured locally at some industrial facility or manufacturing plant. And the question is, how do you ingest it and use that data on the back end to actually create meaningful ML models that can kind of help your cause? And so this is kind of showing, what the core components, if you will, that would make up that virtual cycle. On the bottom left, you have FreeRTOS-powered devices or sensors with Greengrass that's kind of collecting that data and then ingesting that into IoT Core. IoT Core is then forwarding that to services such as AWS IoT Analytics, which can help with the transformation of that data, and then further on ingest that data into Amazon SageMaker to build a model from your collected machine data. SageMaker, again, would be used to optimize that model and redeploy it, or I should say, if it's an initial deployment, pass that on to Greengrass to actually activate a machine learning model for inferencing at the edge. And so the idea is that this process continues on an iterative basis as you continue kind of refining and optimizing your model to the extent that is necessary for your use case. I didn't, you'll notice in the reference design with NXP, we didn't really mention at this point any use of AWS IoT Analytics, but a lot of times, again, when you're dealing with machine data, just based on the volume, variety, and veracity of that data, you do have to do quite a bit of extraction and transformation of that data before it can be usable, even in terms of training your machine learning model. And so analytics is really a purpose-built tool for that. It can cope with copious amounts of machine data that's coming in at a very high rate or high velocity. You can have policies built in to do very mundane type of conversions of your data or transformations of your data, or more sophisticated ones. And then it's also allowing you to kind of capture those data streams in a time series format that can then be used for analysis and or for ingesting into, again, things like SageMaker to build your machine learning models. So let's quickly look at a couple different reference architectures. One of the things that we often have to deal with along with our customers is this notion of tribes. Specifically in industrial environments, you kind of have an operational technology tribe that's very much focused on what's happening, let's say, within the factory. Various protocols come into play. You have SCADA systems, manufacturing execution systems, a lot of black box type systems that do not mean much to your IT systems folks. On the IT system side, obviously you have your usual systems of record or perhaps systems of engagement, and I would argue that a lot of what happens within the in the IT system box or within that perimeter is not necessarily very relevant to the operations technology side. And then obviously where things are running, whether it's on-prem or in the cloud, that kind of adds some more, yet another dimension. And so the idea here is, one of the things that we kind of preach is trying to have effective governance across basically all of the teams, regardless of what camp they fall in. And one way to do that is certainly just to make sure that everybody's involved in what the actual business outcome is, whether that's from a customer perspective, a partner perspective, or even an internal stakeholder perspective. We also deal with quite a common conundrum, which is captive data. A lot of times when you're dealing with on-premises black box type of systems, such as PLC systems or MES or SCADA systems, there's a lot of industrial data that's being collected there over the years, but very little has been done with that data in terms of getting any kind of meaningful insights from that. And so one of the things that we typically recommend as a stepping stone before you even get to the point of what specific machine learning type of application are you going to develop to help your cause is expose that locked data, get it into into a versatile data lake that incorporates industrial data context as well as other data types, and start deploying the tools that's going to give you basically the ability to gradually get from describing or understanding that data to how to use it for an AI ML type of application that you want to develop for your use case. And so this is kind of the common case for an industrial data lake. There's kind of real 4 key points here. One, again, get that full data picture, ingest all that data from your local historian or local MES or SCADA systems that's on-prem. We preach or advocate for a single repository, whether you take that in a literal sense or not. The idea is that you just want to make sure that the right folks have access to the right data, whether that's a fragmented data lake or truly one consolidated data lake. It's really just about access policies and being able to share data with the right folks. Again, right analytics tools for the right job. Basic SQL querying may work for some folks, but maybe for your plant managers or the folks that are less well-versed with, with some of the common IT tools, they may just want, a simple visualization dashboard that they can kind of click and drag through. And then, the point 4 here is just connect internal and external apps. And this is something that you'll kind of see in this next slide, which really just kind of emphasizes the edge to cloud to edge analytics cycle. Again, emphasizing the point that I think the industry gets too caught up in terms of what's happening or what should happen at the edge versus what should happen to the cloud. I think balance is key here. So being able to actually maintain whatever virtual cycle makes sense for your specific operation or use case in terms of taking that edge machine data, transforming it, perhaps doing some local inferencing on that, but still being able to pull it into the cloud so that you're aggregating that perhaps with other meaningful or additive data sets to produce even more interesting insights back to the business or your stakeholders. So there's a couple of reference architectures here. I'm not going to go into detail. These are just kind of illustrative to kind of show you how do you take these different Lego building blocks and put them together, or how can you put them together in later slides. Just for reference material, I'll have some links there for the AWS IoT solution repository, which will actually provide these in terms of consumable code with the associated GitHub repo, so you can actually start experimenting with this in your own environment. These are just kind of illustrative, again, for different manufacturing type of scenarios. Just based on time, I'd like to quickly go over the customer success stories. These are just two examples that I think we find pretty interesting. The first one is Valmet, who's a global pulp/paper manufacturer based out of Finland. And one of the use cases that they came to us with that we helped was really how to start going down the path of building a digital twin for one of their manufacturing facilities, and specifically one of their production lines. And if you think about it, I mean, that illustration there kind of shows all the moving parts and complexity associated with commercial paper manufacturing. You have various rollers, you have various chemicals that are coming into chemicals and materials that are coming into the actual production line. A lot of in-place sensors and actuators already deployed, and so a lot of data was already being captured historically, has been captured within that manufacturing facility, but there really wasn't a lot of contextual awareness to that data. And so one of the things that we did with Valmet was getting them to actually start ingesting that data, again, exposing that data, ingesting it into the cloud using AWS IoT analytics, and starting to actually provide additive capabilities to create a meaningful machine learning model that could do predictive analysis or provide predictive maintenance type of insights to the plant managers at that facility, versus the usual statistical approach, which was depending on well-known asset models for some of the machinery, perhaps for other parts of the machinery, no existing asset models, but being able to kind of synthesize that data and really come up with a predictive maintenance or predictive analytics, I should say predictive maintenance system for the entire production line. So that's kind of a classic, predictive maintenance use case. Another one, which I think is in a way a little bit more transformative in terms of how an existing company that's been shipping, ball bearings for various commercial applications, SKF, also based out of the Nordics. They provide ball bearings for everything from windmill turbines to other commercial or industrial machinery. And so one of the things that they were experimenting with was how could they actually provide better insights to the actual devices their product was going into. And so for a windmill, for example, they would provide not only the bearings, but an automated lubricating system that would kind of monitor the condition of the bearing. And so one of the things that we kind of helped them take to the next level was not only monitoring the condition of the bearing, but I guess through the sensor capabilities that were built into that auto lubrication system, detecting other things that were happening within the windmill, such as vibration, frequency, temperature, and being able to actually provide that through an intelligent dashboard back to their customers. So it did two things. One, it provided kind of ball bearings as a service for their customers. They could know when a ball bearing was about to approach the red territory and need replacement, and they could also provide additional insights to their customers in terms of the overall functionality beyond the bearing as far as the equipment that it was deployed in. So again, transformative in the sense of really being able to support a new business model for their existing customers. So just quick wrap up. There's really we find there's no real compression algorithm for experience, and really what we mean by this in the context of IoT is you kind of have to pick your battles. We really try to encourage customers to avoid the undifferentiated heavy lifting. In the spirit of AI ML, we certainly treat that model development has to be very specific to your use case, or should be very specific to a customer's use case, and that should reflect unique data to them. But in terms of how to wire sensors or how to wire edge gateways and how to actually deal with basic data ingest, there's various services that can already do that for you, right? So from a developer perspective, really trying to focus on kind of the core value proposition to your solution, and look to providers or third-party technologies that can just kind of help you do away with the undifferentiated heavy lifting. And this is just kind of a quick at-a-glance view of all the different services that come into the fold from an AWS IoT perspective. More importantly than just the services themselves, because the services in many cases may not mean much when you're looking at kind of an end-to-end solution. This is the solution repository that I would encourage you guys to visit. We have, it's not just industrial focused, there's a lot of also consumer, connected home, connected smart building use cases in there. And what you'll find is these will actually click to, again, as I mentioned before, the reusable code recipes that you can deploy in your own environment, alter or modify to suit your specific needs. So I highly encourage you guys to visit that. There's a number of different partner solutions that you'll find in there as well, such as those from NXP and Toradex. And then, from a partner ecosystem perspective, we try to play with all of the best of breed providers here, whether it's on the edge component side, on the silicon vendor side, or on the connectivity side, or on the actual solution side, be it ISVs or system integrators. So encourage you to visit that if you're either working with existing partners on a IoT, AIoT solution that you have in scope, or maybe something future down the road. And then the last thing I'll mention here is just the device catalog. Given that many folks here are very much interested in specific hardware types and different architectures, what we've tried to do over the past, I think, 2 years is really be proactive about qualifying and certifying different hardware components, again, whether it's purely silicon vendor or connectivity type of devices, and making sure that they interoperate with AWS IoT so your developers don't necessarily have to worry about that. It's kind of, again, nurturing this mantra to focus on the core value for your specific development use case, and let others worry about the undifferentiated heavy lifting. And the device qualification certainly plays front and center there. So that's it. A few additional resources that you guys can certainly access, whether it's focused on vertical specific solutions for IoT, or if you're looking at simply just getting a little bit more training, coming up to speed on kind of the different AWS IoT and ML capabilities. Certainly encourage you guys to visit some of the resources that we have here. I'll be around if any questions. I think we're right at time, but okay, thank you.